Hello, everyone. I am making some videos to help you with 3.5 and 3.6. This one is going to help you with the in-class worksheet that we didn't really get a chance to do much of. But I wanted you to have a couple more problems to do and some more practice. Um, so without further ado, we'll just kind of work through some of this. So here we are asked to find the first derivative of this function. Now this one's nice because the only operation that we have here is subtraction, and in calculus, subtraction is our friend. We're going to do the derivative of the first minus the derivative of the second, and that will be our derivative. So this is just kind of helping you to practice your derivative rules. The derivative of cosecant of x, this one is negative cosecant of x times cotangent of x. That is all the derivative of cosecant. And then we're going to subtract from that the derivative of cotangent of x. The derivative of cotangent of x is negative cosecant squared of x. And so that is our derivative. From here, we'll see if we can simplify it all. This is negative cosecant of x times cotangent of x plus, right, minus a negative turns into a plus cosecant squared of x. These aren't like terms, they don't combine. They both have a cosecant of x, so I guess you could factor that one out if you really wanted to, but nothing is really going to go away or combine or really get any simpler. So I don't know that this is much better. My brain just would stop here. I like this better than this, but you kind of decide where your brain likes it and likes to stop. So um, that'll just be the answer to this one. Okay, the next one. Find the first 5 derivatives of the sine of x. And then find the 23rd derivative of x. Do I want you to take 23 derivatives to find the 23rd derivative of this function? No, I don't expect you to find 23 derivatives. But I'm having you find the first 5 derivatives because I think we're going to find something in there that's going to give us a clue on how to find a 23rd derivative without actually doing 23 derivatives. So here we go. First 5 derivatives, 1, 2, 3, 4, 5. Okay, so we will go ahead and find our first 5 derivatives. Okay, f prime, the derivative of sine, that's cosine of x. Okay, f double prime, the derivative of cosine is negative sine of x. All right, the third derivative is going to be the derivative of negative sine of x. This is negative 1 times the sine of x. That negative 1 is attached to something with an x in it, so it comes along for the ride. And we're going to multiply that by the derivative of the sine of x, which is the cosine of x. So this is negative cosine of x. That is our third derivative. Now for our fourth derivative, we're going to take the derivative of negative cosine of x. Again, that negative 1 is attached to something with an x in it, so it's going to come along for the ride. And then we have to multiply by the derivative of cosine of x. The derivative of cosine of x is negative sine of x. And a negative 1 times a negative sine of x gives me a positive sine of x. And what's my fifth derivative? Well, it's the derivative of the sine of x, which is just the cosine of x. Okay, so now that we've done these first 5 derivatives, I want you to go back and look at what we just did and see if you notice anything. Well, we started at sine, then we went to cosine, then we went to negative sine, then we went to negative cosine, and then we went back to sine. At my fourth derivative, I was back at my OG function. And then my fifth derivative, well, that was the same as my first derivative, right? My sixth derivative, if I had to find it, well, that would be the same as my second derivative. Because it's a loop, right? I'm going to go from here back up to my original, and then I'm just going to keep going through this loop as many times as I need to, right? That pattern is going to go again. So really, there's a couple of ways to think about this. You can kind of start and say, this is my first, second, third, and then the fourth derivative is going to come back up here, and then say my fifth derivative is back here, sixth, seventh, eighth, and you can keep going. And notice you're always going to come back. So you could keep doing that until you get to 23. And you will eventually find that this is going to be your 20th derivative. This is going to then be your 21st derivative. This then is going to be your 22nd derivative, and this will be your 23rd derivative. So f 23rd will be negative cosine of x. Sorry, I didn't give myself much space there. We can also say that notice we always come back to our original at multiples of 4. So if I'm going to 23rd, I'm always going to end up back at my original at a multiple of 4. So I know that right before I hit 23, the last multiple of 4 before that is 20. That's how I knew that I was going to be at 20 here. You can keep counting all the way out and see that 20 is going to be back up here. Or we can kind of use these patterns to say, oh, I'm always going to end up back up here at a multiple of 4. So 20 is going to be my last multiple of 4 before I get here. And then I can just count 20, 21, 22, 23, and I know I'm going to end up right back at this one. So again, with repeated derivatives, patterns are our friend. And we can use those patterns to find higher derivatives without taking all of those derivatives. Cool. And then the last one here, calculate dy d theta. That means my first derivative for y equals 9 times the secant of theta plus theta times the cotangent of theta. Okay, well, this says find the derivative of y, and my variable is theta. Okay, so to find the derivative of this, we're going to take a deep breath and we're going to kind of get the lay of the land. I have addition here, which is my friend, which says I'm going to take the derivative of this and I'm going to add to it the derivative of this. We'll do it piece by piece. Okay, the derivative of 9 times the secant of theta. Well, that's just a number times something with a variable in it. So the number is going to come along for the ride because it's attached to the secant of theta. And I'm going to multiply that by the derivative of secant of theta, which is secant theta tangent theta. So that's the derivative of the first piece. That's not so bad. And then I'm going to add to that the derivative of the second piece. How do you do the derivative of theta cotangent theta? Well, remember that theta is our variable, and I have multiplication right here, and I have something with thetas on one side and thetas on the other. Since I'm multiplying variables together, that says I need a product rule. Okay, so to do a product rule with this, we're not going to panic. Our process for product rule says I have to figure out what f and g are. So my first function will be f, that's theta. My second function will be g, that's a cotangent of theta. And then I'm just going to find the derivatives of those. The derivative of theta, any variable by itself, the derivative is 1. And the derivative of cotangent, that's negative cosecant squared of theta. And so now we can come back and do our product rule, and we'll do f prime times g plus f times g prime. We are going to get really good at the product rule. For some reason, I went to red, so I guess I'll do this in red. Okay, f prime is here. That's 1 times g, which is up here. That's cotangent of theta, plus f, which is up here. That's theta, times g prime, which is over here, which is negative cosecant squared of theta. And again, use your parentheses. This is multiplication by a negative. That's not subtraction. Be very careful. Use those parentheses. So now to simplify this, our derivative dy d theta. These parentheses aren't doing much. That's 9 times the secant of theta times the tangent of theta, plus 1 times the cotangent of theta is just the cotangent of theta. And then theta times negative cosecant squared of theta is negative theta cosecant squared of theta. I'm just going to move that negative out front. And I don't have any like terms. There's really nothing I can do. That is my derivative. Beautiful as it is. All right, so this was just helping you practice doing your rules with trig functions in them. So hopefully that'll help you with your homework. And to prepare for next week on Tuesday, where we're going to introduce another monster rule. We're going to introduce the chain rule on Tuesday. The hardest part about using the chain rule, much like the hardest part about using the product rule, is finding it out in the wild, right? The fact that we had to use a product rule here, identifying that theta times cotangent of theta needed a product rule, that's the hard part about that. With the chain rule, the hard part about the chain rule is noticing when you need it. And sometimes you're going to get confused between when to use the product rule and when to use the chain rule. So what I want you to do here on this back part of this worksheet is I want you to go through all of this and tell me if what we have is a product or a composition. Okay, a product. A product means multiplication, right? So a product means one function f times another function g. This is multiplication. Or I want you to tell me if it's a composition. A composition of two functions is one function plugged into another function. That looks like f of g of x. And really what I mean by that with composition is that you have an inside and an outside function. And then, so we're first going to identify whether we have multiplication or a composition. And then after we identify whether we have a product or a composition, we're going to identify what f of x and g of x are. Now, for a product, this is what we're used to doing. For a product rule, right, you call your first function f of x, you call your second function g of x. So that's going to be the first and the second functions that you're multiplying. So that's how we're going to identify f and g for a product. With a composition, notice it's going to be f of g of x. G of x is inside f of x. So when you do a composition, f of x is going to be your outside function, and g of x is going to be your inside function for composition. And again, that's going to happen when we have an inside and an outside function. Now, the cool thing about this is that sometimes we will have both, and you can look at something as either a product or a composition depending on how your brain looks at it. So let's start with this first one, x minus 2 squared. Now the question is that two functions being multiplied, or is that one function inside another function? Well, this one's interesting because it could be either, right? If I write this as x minus 2 times x minus 2, that's a product, right? I've got two functions being multiplied because the multiplication is right here. one thing times another thing. And in that case, to identify my f and my g, f is my first function, which is x minus 2, and my g would be my second function, which is also x minus 2. So we can look at it as a product and do a product rule on it if we had to take the derivative. Now, alternatively, we could also look at this as an inside and an outside function. And we could also look at this as a composition. This one could be either. So either of these answers is good here. And the hard part about this is identifying these functions, especially for composition. Now, f of x for composition is my outside function, and g of x is my inside function. I think it's helpful to start with your inside function here. If you look at x minus 2 squared, what would you say is inside something else? What if you had to pick something to be inside something? What's inside something else? Yeah, the x minus 2 is inside something else. So that's going to be my inside function, g of x. Now, what is x minus 2 inside of? Well, it's inside a squared function, right? So the thing, my outside function, the thing that my x minus 2 is inside of, is going to be an x squared function. That is my outside function, and x minus 2 is my inside function. So again, it's inside and outside for composition. So let's do a couple more of these, and then I'm going to kind of let you work because I want your brain to sift through some of these and figure out what's a product and what's a composition. So I'm going to do these next two, and then I'm going to have you do the rest of these for Tuesday so that your brain starts seeing inside and outside function or first and second function for multiplication. Okay, so is this an inside function, an outside function, or is this one function times another function? Well, there's multiplication right here. So we can definitely look at this as a product. So I'm going to say that this is a product because I have multiplication between two things with variables in it. In that case, if this is a product, again, f is be my first one, g will be my second one. So in that case, my f of x will be x squared, and my g of x would be x minus 2. And you might say, well, x minus 2 is inside parentheses, but there's not really a function, there's not really another thing being done to it. If you just look at the x minus 2, it's not being squared, there's no square root, there's no other function being done to that. So even though the x minus 2 is inside parentheses, it's not inside another function. There's not a function being acted upon that. So this is only a product. I cannot look at this one as a composition because there's no function inside another function. So this one's just a product. Okay, how about number 3? Okay, well, do we have two things being multiplied? No, I can't really look at this as two things being multiplied because that's not what a square root means, right? Up here, this exponent of 2 could be rewritten to be looked at as a product. But a root, it doesn't mean two things are being multiplied. This really means an exponent, right? That means 3x plus 7 is being raised to a power. So roots aren't multiplication, it's a power. So there's no multiplication here. So this is definitely not a product. This is a composition. It can't be both. It's just composition. There's no multiplication happening here. And again, we have to figure out what our inside and our outside functions are. So my brain likes to start with inside. So what would you say is inside something else here? Yeah, that 3x plus 7 is inside something else. It's inside a square root. So that's my inside function. And the question is, what is that inside of? Well, it's inside a square root, right? So our outside function is going to be a square root function, which would be the square root of x. Or if you looked at it this way, you could say that's x to the 1/2. Both of these are the same. It just depends on whether you want to keep it as a root or write it as an exponent. Either of these would be your outside function because they mean the same thing. But your inside function is 3x plus 7, and your outside function is that square root function. Okay, so I want you to try the rest of these, and I want your brain to start sifting through, do I have multiplication, two functions of x, something with x's times something with x's, or do I have an inside and outside function? So if you have x's times x's, that's a product. If you have x's, if you have a function inside something else, that's composition. And if it's a product, f of x is your first, x and g of x is your second function being multiplied. If you have a composition, f of x is your outside function and g of x is your inside function. So I want you to go through and I want you to finish this table and start to get your brain into, is it a product or is it a composition mode? So bring that with you on Tuesday. It's really going to help us get our brains in the right mode for the chain rule on Tuesday. So have a lovely weekend, and I will see you next time.